All right, and we're live again. Hello, everybody. Welcome to the second live stream of the Antopanic Institute. We're here today to have a virtual watch party for the Geminids Meteor Shower. So before we begin, a couple of things. As you might have noticed, I'm speaking in English. So we'll be doing this live stream in English today. You're welcome to post your questions in the YouTube chat in either English or Dutch, and our team will pick those up, and then hopefully we can answer those. If there is some technical issue, please do let us know. But also, please keep in mind that there's a 30-second delay on the live stream, so it might take a while for things to be resolved. So, why are we here today? Well, as you might have known, it's the Geminids Meteor Showers. These are one of the most spectacular meteor showers of the year. These are debris of the planetoid Phaeton, which the Earth is traveling to, and we can then see in our night sky. They are called the Geminids because they're in the direction of the Gemini constellation, and these meteors travel at a speed of approximately 125,000 kilometers per hour, so that's really fast. So this is just a quick introduction, and we'll have two speakers today who will tell much more about these. First, let me introduce our team. We have Esther Hanko, which is the outreach coordinator. And we have Kenzie Nemo, which is a PhD candidate and also part of our outreach team. Arkady Pasak, also a PhD candidate and also part of our outreach team. Alex Cooper, also a PhD candidate and part of our outreach team. Then we have Bob Jacobs, who is one of the hosts today, who is sitting right beside me, and myself. I am Oliver Boersma, and Bob and I are both PhD candidates. And that is our team for you tonight. So please do interact with us in the chat. There are also other ways to connect with us. We have a website, api.uva.nl. We also have a Twitter account, uva_api. And you can also email us the old-fashioned way, outreach-astro-science@uva.nl. So let me begin with a brief introduction of our institute. So we're the Antopanic Institute. Our institute has been founded by Anton Pannekoek. He was a famous Dutch astronomer born in 1873. He started his career at Leiden Observatory, and he made major strides in incorporating the laws of physics in astronomy. And so, as I mentioned, he founded our institute. So we're the Anton Pannekoek Institute for Astronomy. We're part of the Science Park at the University of Amsterdam. We were founded in 1921, and we started in the attic of Oudemanshuis Poort, a building here in Amsterdam. We moved many times throughout our existence, and we now employ around 100 astronomers, and we also educate bachelor and master students from all over the world. And interestingly, we publish about 200 reviewed science articles per year, so that's a big output for our institute. So what will we be doing tonight? This is the outline of the evening. We'll start with a roof meteor report by Bob Jacobs. Then we'll move on to our two guest speakers, which we are very happy to host for you tonight. First, we have Ralph Weyers, who is the head of the Antopanic Institute. And then we have Felix Bethuneville, who is the project manager at the NOVA Optical and Infrared Group. Then, after those two talks, we move on to the Astro Quiz. Then we'll show you some archival footage of meteors captured by Aardvark, a radio telescope in the Netherlands. And then hopefully we will also listen to live meteors at the Dwingelo telescope here in the Netherlands in Drenthe. And then we'll end by announcing the Astro Quiz winner. And then we'll also point you to a very nice watch party by the Werkgroep Meteoren, where you can also join and talk even more about meteors. So with that, we'll switch to the roof meteor report. Bob on the roof.
Well, thank you, Ollie. I'm here at the rooftop of the Science Park building in Amsterdam, and unfortunately the weather is terrible. It's very cloudy, so we won't be able to see many Geminids tonight. But behind me you can see the domes that we use for observing here in Amsterdam, and on the other side is the big city of Amsterdam. And if it weren't cloudy, you would be able to see the Geminids going across the sky, but they appear to be coming from the constellation of Gemini in the east. Fun fact: the brightest star of the constellation of Gemini, called Pollux, is the brightest star that we can observe, that of which we know has exoplanet, so it has a planet revolving around it. But something else that you might want to see if the clouds go away is the conjugation of Saturn and Jupiter, because on the 21st of December they get very, very close. You will be able to catch them in one shot of a telescope. This is the closest they've ever been, as seen from the Earth, in over 800 years. Well, it's getting a bit cold out here, so I think I'm going inside again. Back to you, Ollie.
Thanks for that report, Bob. It's a bit unfortunate that the weather is not so good tonight, but we also live in the Netherlands, so what do you expect? Oh well. With that, let's move on to our first speaker of the night. Let me introduce him. He is Ralf Weyers, Professor Ralf Weyers, I must say. He is the head of the Antopanic Institute for a couple more weeks. He's a professor of high energy astrophysics, and he studies explosions around black holes and neutron stars. And he's also very involved in the Aardvark telescope, which is part of the LOFAR radio telescope, for which, and with these telescopes, he looks towards bright flashes of radio on the night sky. And today he will give us an introduction to meteors. So with that, I'll hand it over to Ralf if he's ready. Stop sharing my own screen and then he can share his screen. There we go. And then the floor is yours, Ralf. Please unmute yourself.
Okay. So I just unmuted myself, so that should work now. Well, good evening, everyone. I'll start off with this gorgeous picture, which is actually of the Geminids Meteor Shower over the Chinese Xinglong Observatory a couple of years ago. So all these little streaks you see in between the stars are actually meteors or shooting stars. And if there are so many altogether, you call them a meteor shower. And what you can immediately see is that they seem to all be coming from the same place in the sky. And why that is, I will explain a little later. In this case, that place in the sky is in the constellation Gemini or twins, and that's why this shower is called the Geminids. Let's see. Now I have to, there we go. So what are meteors? Well, essentially they are grains of space debris, quite small, zipping through our atmosphere. And the word meteor comes originally from the Greek ta meteora, which means things in the sky. And for example, also the word meteorology is derived from that, which is also, of course, to do with the sky, with our atmosphere. And it was in fact only in the 19th century that scientists firmly concluded that meteors are not something that is intrinsically something only in our atmosphere, but it has actually something to do with things coming in from outer space. So in a very short summary of what I'm going to tell in the rest of the talk, there are all kinds of things of all sizes orbiting our sun. There are planets, comets, asteroids, and these things go all the way down to sizes of grains of sand and dust. And if they hit the Earth, they do so with a very high velocity. That means they get very hot and, as it were, burn up. And when they do that, they cause a brief glowing trail, and that is what we call a shooting star, or with a scientific word, a meteor. They are mostly only a few millimeters to a few centimeters in size, but the really big ones can be up to a meter or even a bit bigger. Um, they come all the time and often on their own. Then we call them sporadic meteors. Or from time to time, at predictable times, they come in swarms, and then we call them meteor showers. And that's what's going on tonight, for example. Now, there are lots of different words that you may find if you start reading a book about these things or you start Googling. The first word is meteoroid, and that is the piece of rock that you have in space before it enters the atmosphere on the Earth. And in typical definitions, anything between a millimeter and a meter in size is called a meteoroid. A meteor is the phenomenon that you get to see when such a meteoroid enters the atmosphere, zips through it, and glows. A meteorite is a piece of rock that you find on Earth and that is left over from a meteor. So, if that's not usually the case, that a piece of the rock survives to hit the ground, but sometimes it does. And when we find such a piece of rock, we call it a meteorite. Then there is space dust. That's essentially the smaller particles. They typically settle very slowly, and every day tons of such dust actually get added to the Earth. A fireball is a very bright meteor. Typically, we call it a fireball. It is if it is brighter than the brightest stars and planets. And a bolide is an even brighter thing, and typically we call something a bolide if it's brighter than the full moon. Now, let's go back to what I said about the solar system and everything that's in it. You no doubt know about the planets in our solar system, and here I have a schematic in which you see the orbits of the planets drawn to scale. And you see the inner four planets, Mercury, Venus, the Earth, and Mars, also drawn in the right scale relative to each other. And then you see the outer planets, Jupiter, Saturn, Uranus, and Neptune, also drawn in the right scale relative to each other, but not to the same scale as the Earth, because in reality, the biggest planet, Jupiter, is about a tenth of the size of the Sun and about 10 times the size of the Earth. Moons and asteroids come in a great many sizes. The largest moons in our solar system are a few thousand kilometers in size, and the smallest ones are only a few tens of meters. And then everything smaller is also there. Now, it turns out that there is a particular region in our solar system, namely the region between the orbits of Mars and Jupiter, in which there are a particularly large number of asteroids. And that region is called the Asteroid Belt. And here on the right, you see a diagram looking towards our solar system, say from the top down, into the plane of the orbits of all the planets. And there you see in white all those little dots of the asteroid belt. And then you see that there are also a few special groups of asteroids. For example, the Greeks and the Trojans, who are more or less in the same orbit as Jupiter, but either ahead of Jupiter or behind Jupiter in its orbit. Now, those asteroids, the biggest one of them is called Ceres. It was discovered only in 1801. So for most of history, we have not known about asteroids. And nowadays, Ceres, strictly speaking, is called a dwarf planet, which is basically something that is a bit smaller than a planet, but still spherical. And you see a picture on the bottom, you see Ceres looks a bit like our moon, really, a bit grayish and full of craters. And many tens of thousands are now known. Now, there is another belt of such smaller objects, but they're not all that small, and that's called the Kuiper Belt, after the Dutch astronomer Kuiper. And those are objects that are outside the orbit of Neptune. Actually, they start just outside the orbit of Neptune. You see them here as the blue and orange dots. And you see on the left, you see Jupiter, Saturn, Uranus, and Neptune actually on a solar system with the sun in the middle. And on the right, you see a picture with a number of those Kuiper Belt objects drawn to scale. And nowadays, we consider Pluto not a proper planet, but a dwarf planet. and it is only one of many such things that are out there in the Kuiper Belt. It just so happens that we discovered Pluto a long time before the others. Now, then there is even a larger cloud way outside the Kuiper Belt, and that's called the Oort cloud, after the Dutch astronomer Oort, who predicted it in the 1920s. And, you know, the Kuiper Belt is maybe up to about 100 times the distance of the Earth to the Sun, away from the Sun. But the Oort cloud is 2,000 to 200,000 times as far from the Sun as the Earth. And that means that the Oort cloud stretches just about to halfway the nearest star. It consists of many icy bodies, and we think that's where most of the comets come from. So most icy bodies that we see as comets close to the Sun originally come from that Oort cloud. And somehow their orbits are disturbed at some point, and then they get sent into an orbit that plunges towards the Sun, and then we see them as comets. Here you see a beautiful example of such a comet. This is a picture that was actually taken last summer of comet Neowise. It doesn't happen very often that we can clearly see a comet with the naked eye, maybe on average only about once every 10 years or so. So I hope you got a chance to see comet Neowise, because it was pretty special. I know I went out to the beach near my home a few times on dark nights, especially to see it. And what happens really, a comet is a bit like a dirty snowball. It's a relatively loose aggregate of stuff, mostly ices, but with all kinds of pieces of rock and dust in it. And what happens if it gets close to the Sun, it begins to evaporate. And then you see this somewhat curved tail, the brightest tail you see behind it, that actually consists of all kinds of particles of dust and little pebbles. And there is another tail, the bluish, more straight tail that you see, that's a so-called plasma tail, and that consists purely of gas and plasma. But the dust tail is actually quite important for our story, because it turns out that many of the particles that we see later as meteors actually come from the dust tails of such comets. Now, the very smallest stuff you typically do not see as meteors, but if you are in a very dark site, just after sunset or just before sunrise, typically maybe an hour after sunset or an hour before sunrise, then you can sometimes see a pillar of light rising up from the place where the Sun is below the horizon. That's called the Zodiacal Light, and what that really is that is all those little dust particles in our solar system that reflect a bit of sunlight and that you then see on the sky. It's really quite faint. It's sometimes called a false dawn if you can see it, but the chances of seeing it in the Netherlands are pretty slim. You typically have to go to a very dark place to see it well. Now, the meteors that you see, sometimes the shooting stars that you often see loosely in the sky, they often seem to come from one point in the sky, as I said earlier. And here you see lots of them, but you also see a sporadic meteor. You see the brightest one that you see in this image clearly does not come from the same place as all the others. And so even on a night where you have a meteor shower, you can also see some meteors that do not belong to the shower. So they are just individual grains of sand and pebbles that come through our atmosphere. Now, why do they seem to come from one point? Well, that's just a perspective effect. What happens in reality is that the Earth is flying through the solar system, and it's flying towards a cloud of such particles. And so they all, if you look at it from the outside, as viewed from the outside, they all come from the same direction onto the Earth, as shown in the upper left of this diagram. But now, if we look from the Earth to that oncoming host of particles, because of a perspective effect, they're all coming towards us from one direction. They seem to be coming from one point. It's a bit the same as if you're driving along a road and you see a set of telephone poles or trees along the road. If you look in the distance, they all seem to converge on points. or if you're driving through a snowstorm with your headlights are on in the evening, all the snowflakes that are illuminated by your headlights seem to be coming from the same direction. Well, these swarms of meteors that we call meteor showers are actually uh, particles that are all in one orbit. And that orbit happens to intersect the orbit of the Earth. And that means that we go through that trail once per year, once every time when the Earth goes around the sun once. And then we meet a whole host of such particles. And often this is because that orbit is the same orbit as the orbit of a comet. And all those particles of dust that were left behind by the tail of the comet form that cloud that we go through. And so here is a famous example, the Leonid meteor shower, which happens every year around November 17, is associated with comet Tempel-Tuttle. That's the comet of which you see a picture on the right. And that comet goes in a very long elliptical orbit. The closest point of that orbit is closer to the sun than the Earth. The furthest point is just beyond the orbit of Uranus, 20 times as far from the sun as the Earth. And it is that comet tail that causes the Leonid shower. And similarly, as Oliver already said, asteroid 3200 Phaeton is associated with the Geminids in a similar way, but maybe a little more complicated. Now, it's a very high-speed game and also a very high-altitude game. The Earth orbits the Sun at a speed of 29 kilometers per second, and that's a little over 100,000 kilometers per hour. And the typical velocity of those meteors is up to a little more than 2.5 times that, or a little less than half that. So typically 15 to 70 kilometers per second. And if a pebble hits the atmosphere with such a high speed, then it already becomes hot when it hits only very little air, so more than 100 kilometers above the ground. And typically about 50 to 80 kilometers above the ground, it's already completely gone. So mostly these meteors are indeed very high up. And what you see is you see the air of the atmosphere that is shocked and heated by the meteoroid, and that causes most of the glow. And of course, the meteoroid also evaporates when it gets hot, and then that material gets mixed in. And that means that you can sometimes see a little bit of color in a meteor if it's very bright. And that color is because of the particular atoms that are glowing. So if it's mostly nitrogen and oxygen glowing, which comes from the atmosphere itself, it might be reddish. But if it's iron or calcium or sodium or magnesium, it could have another color. And so you can see a little bit about what the meteors are made of by seeing in what color they glow. And in fact, if you can find a piece of rock on the ground that is left over, so a meteorite, then you can of course, discover a lot more about what they are made of. And here you see 3 meteoroids that are cut through, and then you can see what they're typically made of. The most common kinds are either made of nickel and iron, that's one that you see on the left, or they are entirely stony, that is what you see in the center, or they can also be stony iron, they can be a mixture of the two. And one reason why they are so very important is that they are the oldest rocks you can find in our solar system. Our Earth and Sun were born together about 4.6 billion years ago. But because rocks on Earth continually get processed by geology, the oldest rocks that we can find on Earth are only about 3.8 billion years old. And so the importance of meteorites is that they show us material that was formed very close to the birth of the solar system. So it's the oldest stuff you can find in our solar system. And in fact, it's also from those meteorites that you get the accurate system. And that's actually all I had to say.
Yes, thanks a lot, Rolf, for that interesting talk. If you could stop sharing your screen. Thank you. Then I'll start sharing my screen again. Yes, and then I'd like to remind our viewers that you can ask your questions in the chat now, and we'll ask those questions to Felix and Rolf after both of their presentations have finished. And it's maybe also good to note that unfortunately we can't be looking at asteroids live tonight because of the weather, but hopefully we will listen to the asteroids or the meteor shower, I must say. So stay tuned for that. And with that, let's move on to our second speaker of the night. This is Felix Bethuneville. He is the project manager of the NOVA Optical and Infrared Group. And the NOVA is the Dutch School of Astronomy. In this group, he works on the METIS camera, which is a camera and spectrograph, which will be installed on the extremely large telescope, an upcoming telescope, which will be the biggest telescope in the world. He's also an expert on meteors, and he's a member of the working group Meteors. And he will be telling us today about how you observe meteors, and in particular the Geminids. So then I'll stop sharing my screen again, and Felix can share his own screen. Please go ahead and do that now, Felix. Perfect, and I'll mute myself, and then it's up to you, Felix.
Right, so if everything works well, you should hear me now and also see the first slide of my presentation. So thank you very much for inviting me. It is an honor to speak here about meteors. As you have heard in the introduction, I'm mostly an instrumentalist, so I build telescopes and instruments for doing science on all kinds of astronomy objects. I'm an active member of the Werkgroep Meteoren, or Meteor section of the Dutch, the Royal Netherlands Association for Meteorology and Astronomy. And indeed, today there is, if the sky was clear, there was a lot to see. So I will not speak a lot about the physics, but more how you can actually see these meteors and how you can study them. So the first thing I like to repeat is a little bit of the namings. So we spoke about comets and asteroids, the bigger pieces in the solar system, which are the source or the origin of all these meteoroids, which eventually can enter in our atmosphere, give light then, and are meteors. And if we have a bigger one and we have some luck, a little piece could land on the Earth. Now, that's not the case for the Geminids. That is a shower which has not this big thing, so please go not outside and look at these. The Geminids is a very special shower because most of the meteor showers we have a comet as parent body. For the Geminids, that's not the case. The asteroid Belt is the origin of this. So that makes it a very special shower. And together with the Perseids and the Credentids in August and January, the Geminid is these are the three big showers which you can see every year. So I start now with a nice little movie to show you once again what a meteor or shooting star is. And I'm pretty sure you have seen that once or many times in your life. It is very exciting to see such phenomena. And you can, of course, do a wish if you wish so. Now, many amateurs and professionals make pictures. Here's just an example of a meteor taken with a Dutch camera network. I come back to that later. And wherever you Google, you will find very exotic and nice pictures of meteors, and sometimes very bright ones, like here, a fireball. They can even be extremely bright, like this one, which was in 1972 with a normal film camera captured at the daytime. And more recently, in 2013, a very bright one appeared over the city Chelyabinsk in Russia. And what you see here is not a fireball, but the cloud which is generated by condensation of humidity in the high atmosphere. And this one was the biggest event in many years, caused the landing of a meteorite and also many damage in the city. So then comes the question, how can we observe them? And I have selected 3 areas which I want to present to you. So the most common and maybe even most important one to do is just watching them with your naked eye. We call it counting. I will also say a bit about radio observing. Last but not least, photography of meteors is also something I want to speak about. So the first thing is counting meteors. It looks romantic, and that truly it is. You do not need a telescope or any other equipment. You just select a dark place and you start counting the number of meteors, and in this case the number of Geminids which you see in a certain time span. And that is very important if you can do that. And there are worldwide hundreds of people who do that. So also this night with the maximum of the Geminids, and that information is all collected. The result of that I have here illustrated in a plot where horizontally you see the date and vertically you see the amount of meteors you could see under ideal circumstances per hour. And all these blue dots are observations. And what you can see clearly is that going through the timeline, every digit here is 1 day. You see that the activity increases and then it goes down. And that is, of course, while the Earth passes the meteoroid stream. Now, why is this important? I have here the NASA logo. It is not that NASA collects this data, but this information, based on standardized visual counting, is used by NASA to calibrate their meteoroid models. And that is just done by trained observers. And you all can learn that to do that. I showed you already asteroids and comets. Here you see another picture of the solar system, and here is nicely indicated the stream of the Geminids. I have here now a movie of the same, and what you see here now is that this stream is not a static thing in the solar system, but like the planet, it also rotates. And that is very important to realize, because the planets which you see moving in the circles, they cross every year that stream. So every year at the same date we see the meteor shower, but we do not see the same piece of the meteor shower. We make an other cross section, we see it at an other moment in time. And by combining all this information from each year together, we can construct a model of how the meteoroid stream in the solar system is. And therefore it is so important to do every year these observations. Now, unfortunately, this is not clear here in the Netherlands. We cannot do much, but trust me, in other places, other locations on Earth, observers are working now as well, and they collect data. The second method of seeing or taking evidence of meteor is radio. And that sounds very exotic maybe, but also that is easy to do and easy to understand. Radio transmitters, which you see here in the left, you have everywhere, radio stations, in the past TV stations, but also scientific transmitters. And you have to realize that these meteors, they are of ionized air and they can reflect radio waves. That means that if the transmitter emits a radio wave, it can be reflected and received by an antenna which you have on your roof or in your garden. You can even hear the signal if the transmitter is below the horizon, as indicated in this plot. A radio antenna is pretty simple to build yourself. The radio receiver is a dongle nowadays, and that way you can see, you hear noise. You will hear that later also in this stream. And you can, the tiny 3 peaks you see are real meteors. Then I like to go to photography. This is also a picture taken by myself of the Geminids in 2017 at the International Observatory in Paranal. And you can do that with every camera which is able to make long exposures, a few seconds or more. But it becomes far more interesting if you have 2 cameras on 2 locations about 50 to 100 kilometers apart from each other, and they point at the same spot about 100 kilometer altitude in the atmosphere. If you do that, you can capture the same meteor with 2 different cameras, so 2 different backgrounds. And by doing triangulation calculations, you are able to reconstruct trajectory in the atmosphere, so you know exactly where it was in the atmosphere and also which direction it had. Now that many people do, also in the Netherlands. I have here a map of the Netherlands with all video stations working every night. This one is the CAMS Benelux Video Network, initiated by NASA, operated by the Dutch Meteor Society, and they collect lots of meteors every night, and they cover together the entire atmospheric volume above the Netherlands and Belgium. There are simple, very light sensitive security cameras, and with that you are able to point exactly where the radiant is. You can capture the light curves, you can tell something about the brightness and the altitude where they are. So this gives a lot of information on the characteristics of the meteor shower. There are also people who build special camera with very wide angle optics, fisheye lenses, and these are very well suited to capture fireballs. Here is another network in France where they operate it also. And there is even an exciting example of a fireball network in the Australian desert, where if a meteorite is dropped, you are relatively easy capable of retrieving them. And I could not resist to add also a picture of Antarctica, where maybe it is the easiest place to find meteorites, although if you find it, you have not yet traced back the orbit where it is coming from. Now, instrumentally, I want to add one other thing. That is such a camera you can also build yourself very easily, but there is one special addition, which is an optical shutter which closes and opens very fast. And that makes that the meteor is not a trail, but a dashed line. And that we do because we can then estimate the duration of the fireball and therefore also the velocity. And if you know the velocity, you are able to construct the orbit of the original meteoroid in the solar system. Now, this is all exciting, all this modern technology. Is it important to report your fireball? Yes, it is. It is very important. There are websites, both international and also in the Netherlands, where you can report every fireball, bright meteor you see. And I give here an example of a fireball which happened very recently on the 20th of November. More than 500 people in the Netherlands saw it and reported that. And based on this information, we are immediately able to reconstruct the trajectory. And with all the photos, dash cams, and news attention, we cover them. We have a very good description of what exactly happened. Now I come closely to the end. One of the things we do is calculating very precisely the velocity and also the deceleration, so the decrease of the velocity, and with that we are able to calculate the mass and whether there is something left over. And if that is the case, we will set up whole search expedition to see whether we can recover something. Now, as said before, this happens only with bright fireballs from asteroidal origin, and the Geminids, although they have also an asteroidal origin, they are not known of dropping any meteorites. Now, how many meteorites do we have then in the Netherlands? Is that unique? Is that rare or not? Yes, it is. We have only a handful of meteorites in the Netherlands. Most of them are very old. The most recent fell in the north of Amsterdam in 2017. It's called the Broek in Waterland. And if you found a very weird stone, please check the internet then and check whether it could be a meteorite or not. And if you think it might be, you are always able to contact us or one of the universities, and they will help you in telling whether it was a real meteorite, which then, of course, is very interesting. Now, my very last slide. Finally, the Geminids 2020. What can we expect if it was clear today? I made here a plot where you see horizontally the time of the during the night. So we are now at 9 o'clock, more or less, a bit later. So we should expect now 50 meteors per hour under dark conditions. That goes still a bit up during the night, and in the middle of the night, 2 o'clock, we should reach the maximum amount which we could see. And it is so sad that we are, of course, now on the cloud cover, so it is not so easy to see them, and only radio remains to have a look. But maybe next year you have another chance.
Great. Thanks, Felix, for that another very interesting talk. Let me share my own screen again, and then we move on to the questions for Felix. And so we already have a couple ones in the chat, and please feel free to ask other questions in the chat, and hopefully we can answer them here on the live stream. So we have from Alicia for Felix. Have you ever personally recovered a meteorite? If so, how big was it?
Yeah, that's indeed a very nice question. I have participated in quite a few search campaigns, but so far that has not been successful. The two last meteor droppings in the Netherlands, the Broek in Waterland and the Glanerbrug, that were both meteorite droppings which went through the roof of a house or a shed. So the meteorite was found first, and I was involved in the calculation of the trajectory. So that's the other way around. So the answer to this question is no, I have not found a meteorite myself based on the work we do.
Okay, thanks for answering that. That's a pity. Maybe sometimes in the future. We have another question, and that is from Win Mobile. He asks, can you derive from a radio signal whether a meteorite is a Leonid, a Geminid, or can you not do that? I think to both our speakers, this is the question.
Oh, maybe I can try to answer that one. The difference whether it's a Leonid or a Geminid, you can tell just from when it happens, because the peaks of those showers are a month apart. So just from knowing when they happen, you know what it is. Typically, you can't derive directly just from the radio noise signal. You can't derive very much of whether the specific meteor that causes that reflection belongs to the swarm or not. But because in the night of a meteor shower, almost all the meteors belong to the shower, you can still get a good count of the shower that way.
Okay, yeah, that makes sense. And so a bit of a follow-up question on that. Are all meteor showers an annual event?
Yes, I believe so, but Felix knows better.
Yeah.
They're not always equally strong.
No, indeed, they are always annual in the sense that if the Earth crosses that orbit, it is very likely that happens next year as well. But if you look at longer time scales, then you have to say that this orbit of the meteoroids is not necessarily stable. So the Geminid is here a very good example. In 200 years from now, we cannot expect strong showers of the Geminids anymore. They simply do not cross the Earth's orbit anymore. And then secondly, what Ralph also said already, the strength of the shower can be very variable. That you can explain that the concentration, the density of the dust particles over the comet orbit is not constant. And here the nicest examples are the Leonids, which peak every 33 years, and in the years in between they show a very marginal activity.
Very interesting. And so what are currently the easiest meteor shower to see?
Yeah, so the Perseids, the Geminids, that are the both very good showers, which are very reliable. You can, if the weather cooperates, you can be assured of a nice show. And the third one is the Quadrant shower, early January, so that is also coming soon. But that is always in the early morning hours, and it is harder to, you have to wake up early, harder to see.
Okay, thanks. We have another question from Eline. What is the difference between meteoroids and meteorites? And I think I heard Ralph talk about this in his talk.
Yeah, so the meteoroid is the rock that is moving through the solar system and that is still untouched by our atmosphere. So that's the thing you begin with. And the meteorite is the thing you find on Earth after it has gone through the atmosphere. And so one very important difference between the two is that the meteorite will be a lot smaller than the meteoroid because a large part of it evaporates as it is moving through the atmosphere. And Felix was showing that you can actually calculate how the mass changes. So he can probably be a bit more precise about how much mass you have to start with in order to be left over with a certain something.
Yeah, that you can calculate that, and there are many parameters here: the velocity and the steepness, how the trajectory enters the atmosphere, as well as the density and strength of the meteoroid. If the particle was very big, then there is also a higher chance that much survives. Mostly it is zero, but of a typical meteorite which you find, I would say it is in the range of percents. So only a few percent of the initial mass survives.
Okay, thanks. And Wilfred asks, is it possible that there will come new meteor showers in the future from exploding stars perhaps, or collapsing planets?
Well, maybe not from exploding stars or collapsing planets, but it is certainly true that in the same way as Felix just said that the orbit of a meteor shower doesn't have to be stable. And that means that one that is now intersecting the orbit of the Earth will probably not continue to do so forever. So at some point it disappears. But in the same way, it is possible that a debris trail orbit that does not now intersect the orbit of the Earth later will. And I believe I read, but I'm sure Felix knows this better, that we became aware of the Leonids and their very spectacular showers for the first time only in the 19th century. So it is quite possible that is an example of a shower which during historical times first appeared for the first time.
Yeah, that is correct. There are also showers which we know already back to from the Chinese history. So there are also examples of more stable showers. And what is very interesting nowadays, we are able to study better and better comets, and also how the ejection processes of comets occur, and we are able to simulate from that forecast whether new showers may appear in the future. And so it is likely that in the future we can make predictions that we can see on certain nights showers which we have not seen before.
And do you know perhaps when there will be a new meteor shower, which we will have not seen before?
There are a number of examples. I have to look them up, and all of these, they were small, so they cannot compare with the Geminids or the Perseids. Maybe one exception. But of course, we are looking very much forward to the next return of the Leonids around 2033. And the years around, and that would be the next very exciting event to come.
That's great. And so then we have one last question. How do you know how old these rocks are?
The way you can measure the age of those rocks is actually a little bit complicated. You do it with radioactivity. Essentially, what happens is that you have to find some unstable elements like uranium and thorium in those rocks that are long-lived, but they don't live forever. And so what you then do is you measure how much, for example, uranium is still in the rock. You measure how much of the decay products of the radioactive uranium are in the rock. And by comparing those two, you can discover how long ago the rock was formed and uranium started decaying in it. And there are many things you have to correct for when you do that. So it's not a simple measurement, but eventually you can do it that way, and that's how you measure the ages of rocks.
And how precise can we get via that method?
Well, up to a few, for those very old ages, up to a few tens of millions of years. So I think the most accurate age for the solar system is 4.58 billion years, plus or minus 0.02 or so. So it's pretty good.
Yes, that does sound pretty good. And it seems that I actually missed one question from Danielle Bakboord. Does this meteor shower bring any danger to the International Space Station?
No, this one not, but it is a very good question because this is exactly the reason why NASA is so interested in meteors or meteoroids, because they want to understand when there come events which possibly are dangerous for spacecraft, the International Space Station or satellites in general. And but the normal Perseids as well as the Geminid meteor showers, they are not strong enough to cause serious damage. Of course, it is a matter of chance. You can never say sporadic meteors, which are in frequency much less, but they could cause damage. But the chances are, due to the Perseids and the Geminids, small.
Okay.
You do find minor amounts of damage to satellites that have been up for a long time due to micrometeorites. So there's those little dust specks. If a satellite is up long enough, it always gets hit by a few, but usually those are not powerful enough to really do lethal damage to the satellite. So you find little dents and specks, and maybe occasionally a little bit of a solar cell gets hit and knocked out, but you have enough of those.
Okay, very interesting. And I think that's a good note to end this discussion on. And so I'd like to thank again Rolf and Felix for their very nice talks and the interesting discussion afterwards. And then we'll move on with our program of the night. So thanks both again. And the next part of our program is our famous Astro Quiz. And so for this, we'll put an answer form in the YouTube chat. So please do fill in your answers in that form and do not answer the questions in the chat, so then everybody gets a fair chance to play along. And also, please try and answer the questions yourself and not, for example, Google them. Then we keep it fair and fun for everyone. So then I think I'll wait a couple of seconds for people to get their answer form on their computer. And then after that, we'll start with our Astro Quiz. And if you manage to win the Astro Quiz, you get a very nice prize. And you can contact us afterwards if you are the lucky or well-educated winner of this Astro Quiz. So I'm looking over to the right. Has the form been posted? Okay, I think then it's time to get started. Question 1. At what velocity does a typical meteor enter the Earth's atmosphere? A. 72 kilometers an hour, B. 7,200 kilometers an hour, or C. 72,000 kilometers an hour? And you get 20 seconds to answer the question in the form, so not in the chat. Please answer them in the form. 5 seconds left. And we move on to question 2. Where do the meteors from the Geminids come from? A. From debris shed by an asteroid. B. From the material expelled by a supernova. Or C. From the remnants of space trash. Again, 20 seconds. Where do the meteors from the Geminids come from? And so, if you're a good listener, you might actually have heard some of these answers of the quiz already tonight. And we move on to question 3. Why is this meteor shower called the Geminids? A. Ancient astronomers believed them to be sent alien Gemino gods. B. They appear to come from the direction of the Gemini constellation. Or C. Meteor showers, like hurricanes, are named in alphabetical order and Geminids was chosen. 20 seconds to answer the question in your form. Please refrain from answering the questions in the YouTube chat, but answer them in the form and you get a chance of winning our prize. And we move on to question 4 of our quiz. Which of the following words describes an object that makes it through the atmosphere and collides with the Earth? A. Meteor, B. Meteoroid, or C. Meteorite? Which of the following words describes an object that makes it through the atmosphere and collides with the Earth? It's also a good point to mention that we can only send the prize to people in the Netherlands. So if you're not in the Netherlands, do please play along, but we are not able to send you the prize. Question 5. Approximately how many meteoroids and micrometeoroids enter the Earth atmosphere every single day? A. 25, B. 25,000, or C. 25 million? How many meteoroids and micrometeoroids enter the Earth atmosphere every single day? Question 6. In the Great Leonid meteor storm of November 1833, what was the peak number of meteors per hour? A. 100 per hour, B. 1,000 per hour, or C. 10 million per hour? Oh, is this going? There we go. What was the peak number of meteors per hour? Question 7. In 2013, a 20-meter wide massive object entered the Earth's atmosphere over Russia, leading to a meteor brighter than the sun. But how heavy was it? A. About as heavy as a car, approximately 2 tons. B. About as heavy as a blue whale, approximately 100 tons. Or C. About as heavy as the Eiffel Tower in Paris, approximately 10,000 tons. 20-meter wide massive object. How heavy was it? It's a difficult question. Question 8. How large was the crater left by the meteor that led to the Cretaceous Tertiary Extinction event? I hope I pronounced that right. That ended the reign of the dinosaurs. A. 20 kilometers. B. 200 kilometers. Or C. 2,000 kilometers. Five seconds left. 3, 2, 1. And we move on to question 9 of our quiz. How much energy did the dinosaur ending meteor produce when it collided with the Earth? A. 10 kilotons of TNT. B. 10 megatons of TNT, equivalent to humans' most powerful nuclear bombs. Or C. 10 million megatons of TNT. How much energy did the dinosaur ending meteor produce when it collided with the Earth? Question 10. Why do some meteor trails appear colorful? A. The colors are caused by the ionization of molecules on the meteor. B. The colors are caused by light refracting in the atmosphere on path to us. Or C. The colors are caused by shocks that form behind the meteor. Why do some meteor trails appear colorful? Two, one. And with that, the main part of our quiz ended. And in the case that there are multiple winners, we have a tiebreaker question. And that person who comes closest to getting the answer right wins our quiz. And our question is, guess the mass of this meteorite named Hoba that landed in Namibia in 1921. The mass of this meteorite named Hoba. It's pretty big. All right, and that is the end of our quiz. In a few moments, we'll close the form where you can give your answers. So be quick, give your final answers, and then we'll close the form. We'll look at the forms and see who is our winner of the night. And in the meantime, we have some time to look at some meteors and also listen to some meteors. And to look at some meteors, we'll be using observations of aardvark, which is a real-time transient detector based on LOFAR, which is a low-frequency radio telescope, which you can see part of here on the right in the Netherlands. And it's not so certain what we are actually looking at when we look at a radio detection from these meteors. Are these perhaps reflected radio wave from Earth? That's quite likely. Maybe they are radio waves from the meteors itself. And so aardvark is actually currently observing, if I'm not mistaken, to find this out. And we have some spectacular archival footage to show you. And so, Ralph, this may be a bit unexpected, but would you mind actually giving some comments to this archival footage. I think you are very well suited for this.
I probably can. I'm not aware of exactly what the footage is that we're going to see, but if you just show it, I'll try my best and comment.
Yes, definitely. So we'll put up the footage now on the live stream. Hopefully you can see it.
Then I have to go to the YouTube
Right,
channel.
that takes a while. So our viewers should be already able to watch the video, and then in a few short moments we'll also give some comments.
Ah, yes. Yes, and so there is a delay, but indeed we can now see a small part of the. So what you see here is you see a small part of the sky. So it's a little cutout from the observations near the horizon. And what you see is you see suddenly these bright trails appearing in the image. And then you see that the trails actually, they shrink, but they stay for quite a while.
And why do they stay for a while?
The reason why they stay for quite a while is that the trail of hot air that is heated up by the meteor is actually it stays hot for a while. It takes time to cool. There are also winds up there, so you can also see that the trail moves a little bit relative to the straight lines. The lines you see are a grid of coordinates, and so the reason why the trail is moving is basically because there are winds also that high up in the atmosphere, and they make the trail slowly move relative to the Earth.
Okay, very interesting. And so we have one more video to show. So of course we have a little bit of a delay, but it's also an all sky image where you can also see a trail of a meteor. Actually an observation of this year, also by Aardvaag. To look a little bit closely, but you can see it.
Yeah, so here is an image. So this is indeed an all sky image. So this is like the radio version of a fisheye lens. So the outer rim of the image, of the circular image, is really close to the horizon. And so indeed in the bottom right, you see very quickly on the top right, you see a flash. But then on the bottom right, you again see a very bright radio trail. And you see that radio trail also slowly move and change in shape. And that's because of those winds that happen at those high altitudes. So they make the trail slowly blow away.
Okay, thanks a lot, Ralph. Those are all the videos we have of Aardvaag. And then we'll move on to actually listening to meteors, and we can do that live. Hopefully, that is possible. And here, if you would mind going to the presentation first, Bob. Yes, I'll explain a little bit. Yes, thanks. And so these are live recordings of radio signals from meteors live at the Dwingelo Radio Telescope site. And Felix explained this already a little bit earlier in his talk. And they have a radio receiver there that listens to the radio signal reflections of a meteor. And so what you hear is mostly noise, but if we're lucky, you can hear some kind of pew signal through all this noise, and that is actually the reflection of a radio signal on a meteor. So I'll mute my microphone for a bit, and then we'll go listen to this. It's a little bit loud, so you may want to turn down your volume and listen very closely, and maybe you can actually hear the reflection of a radio signal on a meteor. Okay, hopefully you heard a meteor through all that noise. Really quite fascinating that we can listen to meteors in that way. And we'll share the link to that site in our chat, and so you can go have a listen yourself as well later tonight. And I think we have a winner of our quiz. But first, let's go to the answers of our quiz. We'll go over them. Question 1, at what velocity does a typical meteor enter the Earth's atmosphere? This is 70 to 1,000 kilometers per hour. Question 2, where do the meteors from the Geminids come from? They actually come from debris shed by an asteroid. Question 3, why is this meteor shower called the Geminids? Well, they appear to come from the direction of the Gemini constellation. That's why we attach the name Geminids to them. Question 4, which of the following words describes an object that makes it through the atmosphere and collides with the Earth? This is actually C, a meteorite. Question 5, approximately how many meteoroids and micrometeoroids enter the Earth's atmosphere every single day? It's quite a mind-boggling number. This is 25 million. Unbelievable amount of meteoroids and micrometeoroids which enter the Earth's atmosphere. Question 6. In the Great Leonid meteor storm of November 1833, what was the peak number of meteors per hour? 100,000 meteors per hour. Unbelievable number again. Question 7. In 2013, a 20-meter wide massive object entered the Earth's atmosphere over Russia, leading to a meteor brighter than the sun. But how heavy was it? About as heavy as the Eiffel Tower, so that's 10,000 tons. 20-meter wide object. Question 8. How large was the crater left by the meteor that led to the Cretaceous Tertiary extinction event that ended the reign of the dinosaurs? B. 200 kilometers. Question 9. How much energy did the dinosaur ending meteor produce when it collided with the Earth? C. 10 million megatons of TNT. Question 10. Why do some meteors trails appear colorful And the answer is the colors are caused by the ionization of molecules on the meteor. And so that were our main questions. And then we had the tiebreaker question. Guess the mass of this meteorite named Hoba that landed in Namibia in 1921. It's actually 66 tons. And so those were the questions and answers of our quiz. And it looks like a winner came out. And so the winner is, I only have a first name, Iris, or Iris, I'll probably say. So if you're Iris and you submitted your answers, congratulations, you won. Please do contact us via either our social media channels or email, and we'll work out how we can send you the prize. And so one thing I see here um, by messages from the team is that we were actually listening on the wrong frequency where we're trying to listen to meteors. Oh, that's a little bit of a shame, but fortunately, we have now tuned in to the right frequency. So let's give it a second try. Oh, that was great. I think we actually heard a meteor. It's really nice to end our live stream on that. So once again, our winner is Iris of the quiz. Please do contact us and we can work out how you get the prize. And then the final thing I end on is that there's actually a virtual watch party continuing at approximately 11 tonight after this live stream of the Werkgroep Meteoren, the working group Meteors, which Felix is a part of. And here is the link where of their website. And on this website, you can actually find a link to a Zoom meeting. And there you can join the people and have a nice discussion about meteors and have a virtual watch party with other interested folks. So I think that's it for now. Thanks again, everybody, for watching the live streams. We really do enjoy making these. Check out our social media channels and we'll post when we'll do a next live stream. And so with that, I'd like to thank our speakers again for their great presentations. And then I wish you a very good night. Hopefully you can catch some meteors with your own eyes. All right. Bye, everybody.